So I'm very glad to be here for my very first presentation for my PhD. So yeah, I'm a PhD candidate at the Zurich University of Applied Science, and I have a background in statistics and machine learning. And my main research topic is actually to apply those to air traffic management. And so that's why I present you today my first work, which is synthetic aircraft trajectories generated with multivariate density models. It has been co-written by Jérôme Morio and Xavier Olive from the ONERA in Toulouse, and Benoît Figuet and Raphaël Monstein from the Zurich University of Applied Science. First of all, why do we want to generate trajectories? This is pretty simple, actually. So my main research objective is to estimate even probabilities applied to aircraft collisions in terminal and maneuver areas. And this is particularly useful for one problem we had in the Zurich airport, which is the Gato's 1416 problem. It actually states that the go-around trajectory for the runway 14 in red here on the graph is actually intersecting the departure procedure for the runway 16. So it decreases a lot the capacity of the airport, and being able to predict the collision in those cases could be really, really useful for the airport management. So one possible method to do that is called the Monte Carlo methods. So those are pretty simple in the idea. So we just sample a couple of trajectories, one red and one green or blue. We count the number of collisions that occurs. And finally, we deduce the probability we want by dividing the number of collisions we observed by the number of flight hours. But in reality, this is way more complicated because we don't observe any collisions, or of course. So we could sample an infinite times of a couple of trajectories and without any observing any collisions. So in the end, the estimation of the probability is hugely inaccurate. So one way to avoid this problem is to resort to what we call importance sampling. So in our case, it just actually generating artificial trajectories that are very resembling to existing one, but that are typical enough to lead to collisions. So in that way, we could observe more collision and have a better estimation of the desired probability. So for my presentation, the outline itself. So first of all, I will present the data and the representation of the trajectories we used. Then I will present shortly what multivariate density estimation models we used for the flow of trajectory we considered. Then the metrics we use also to evaluate the characteristic of the generated trajectories. And finally, what are the results we obtain and how we evaluate the generation process. So in the literature, we mainly have two philosophies to generate trajectories. The historical one, which is the model-driven methods that are mainly based on flight dynamic equations. So they have the good idea of guaranteeing the physical properties of the trajectories because they actually follow a law of physics. But the drawbacks here is that they are mostly deterministic. That is to say that for a given set of parameters, we can only generate one trajectories at a time. The uncertainties are not really considered in those models, and they are often rely on simplifying assumption of reality, which is sometimes pretty problematic. So alternatively, we have the data-driven methods that are based on statistical models. And they actually imitate the statistical properties of the existing trajectories and try to reproduce them. The advantages here is that the uncertainties like ATC actions or weather uncertainties are actually modeled within those models because they are present within the database we use to train our model. But the main drawbacks are that the flyability and the realism of the generated trajectory are not guaranteed because we are not completely sure that the generated trajectories are actually following the law of physics. And also, depending on the model you want to use, large amount of data could be required, and this also can be problematic at some point. So here, of course, we focused on the data-driven methods, and we worked on the go-around trajectories in Zurich Airport for runway 14 between January 2017 and December 2019. As I said, those are very useful for the Gato 1416 problem. for the sake of this work, we only considered the lateral shapes of the trajectories, but we will see in the future work how can we extend this generating process for more complex description of trajectories. And in our database, we had 407 clean trajectories. So what I call clean trajectories is that is a trajectory without any holding patterns that begin and end at the same points. And so basically that's what you see here on the comparison between the two flows. So once we have our database, we want to find a suitable way to represent trajectories. As we are working with lateral shape of trajectories, we actually need to describe a trajectory of 30 points, for instance, 60 features, because we need for each point X and Y coordinates. But in reality, estimating 60 features with multivariate models is pretty difficult. So we want to reduce the number of features we want to use to describe the trajectories. So we find this way actually. So we select a reference trajectory here on blue, and we discretize it into the desired number of points. So here we selected 30 points. And we draw in each of those points the normal lines to this trajectory, so the perpendicular lines. And we discretize the other trajectories by selecting the intersection between those lines and the trajectories. And then we project those intersections onto the corresponding normal lines to go from 2D representation of a point to just a scalar. So as a result, we have something represented as in the slide. So every point number here are actually located on the same lines. So this is very intuitive. And also we can get, of course, the lateral representation X and Y from ZE and the other way around also pretty simply. It reduces the dimension of the representation of a trajectory by a factor of 2. So if we have a trajectory of 30 points, we just need 30 features to describe it. So a trajectory is represented by just a vector of 30 scalars here. So we have our suitable representation of trajectories. So then we want to model the multivariate distribution of the set of trajectory we have. So multivariate distribution for the non-statistician people, those are just distributions that model random vectors. So we call also for the vocabulary, the marginal distribution, the univariate distribution that are used to model each of the coordinates of the vector separately. So on the graph here, for instance, we have pretty much the same representation as before, but with the marginal distribution. So for instance, here for the 24th marginal distribution, we just have actually the univariate distribution of the position of the data set of the trajectories along the 24th line. And so mathematically speaking, also, we considered that a trajectory is actually a realization of a random vector. So to formulate the problem mathematically, we just have a random vector z that is following an unknown density g. And the goal here is to find a good estimate of this density g that we call g hat. And we, of course, find it with the data set we've constructed before. And once we have this Gauss estimate g hat, we can usually generate new trajectories by just sampling from this new density we estimate. So way to estimate this quantity g hat, actually there are plenty of them, but we focused here on the most common ones. Of course, the first one is to resort to Gaussian distribution. They are very simple. They are very well known by statisticians. They don't require so many parameters. So they're very, very useful to use. So we first try to fit a Gaussian distribution of data sets, but of course they are simple and they rely on very strong assumptions. Like for instance, every of the marginal distribution should be Gaussian also, which is clearly not the case here. Like for instance, in the middle of our distribution, in the middle of our trajectory, sorry, we don't have any Gaussian distribution at all. So to improve that, we could resort to what we call Gaussian mixtures. So that's also very simple. We just have several different Gaussian and we sum them up to have a more complex density models. So here's the example of a Gaussian mixture with fixed components. So the addition of 6 different Gaussian with different parameters. And in the end, we have actually a more complex density, but also very simple to describe. Alternatively, we have also in statistics a very useful tool, which is called the statistical couplers. So they're very useful because they decompose the problem, which is pretty difficult, into two simpler problems. The first one is to estimate each of the marginal distribution independently. This is pretty easy because estimating a univariate distribution is actually easy. You don't have the high dimensions curse. And then once you have those marginal distribution, you just have to estimate the dependencies between the marginal distribution with what we call a coupler functions. Intuitively, in our case, coupler functions makes the choice of the position I of the trajectory relevant with respect to the past of the trajectory and the future of trajectory. So it avoids having, big wiggles into trajectories, which is not realistic at all. Finally, for the theoretical part of the presentation, we present here the metrics we use to assess the quality of the generated trajectories. So the Mahalanobis distance based on the trajectories. So those are distances based on between trajectories, sorry. This is the Mahalanobis distance to the mean trajectory. So this represents the ability to generate mainstream trajectories that are in the belly of the distribution. The mean Mahalanobis distance to every real trajectory. So those are more the ability to generate trajectories that resemble existing ones. Then we have maybe the most important metrics here, the E distance, which is pretty much the distance between the real distribution G and the distribution G hat we estimated. So we have to be, of course, a close estimation of the real distribution we wanted. And finally, we have a metric to evaluate the shape of the trajectory, if they are realistic or not, which we actually count only the number of turns of the trajectory, because we noticed that actually a real aircraft trajectory is mainly composed of straight lines. And so if there are two wiggles, there are too many turns and they are not really realistic. So here are the results of the generated flows with different methods. So on the top right-hand corner, we have the real trajectories for the go around. And then first, we have an estimation with the coupler model without the dimensionality reduction we've presented before. So with the 60 features, we estimated for each point X and Y. And then we have the coupler model with the dimensionality reduction and the Gaussian mixture with the dimensionality reduction also. And the first thing we see here is that it looks like with the dimensionality reduction, so when we estimate less features, the generated flow seems to be a lot more realistic than without the dimensionality reduction. So this appears to be a good point. And we will confirm this by the different metrics to assess the quality of the results. So first of all, we actually noticed that decreasing the dimension actually increased the goodness of fit, which is described here for the E distance. We see that for given methods, when we apply the dimensionality reduction, here dr, we actually have a better E distance, so a lower E distance. So that means that the goodness of fit is actually better. But also, when we look at the number of turns, we see that when we apply this dimensionality reduction methods, we increases the wiggliness of the trajectories. So even though the trajectories are better estimated, it also appears that the generated trajectories, when we apply this method, are more wigglier. And then when we look at the Mahalanobis distance to mean, so the ability to generate mainstream trajectories, we see that the couplers models actually generate trajectories that are more atypical. That's not necessarily a problem. That just tells us that depending on the model, especially with the Gaussian mixture and the normal distribution, it put more weight on generated trajectories that are in the belly of the distribution, whereas the couplers allows to have a broader scope of generated trajectories. And then when we look at the ability to generate trajectories that resemble to existing one, we actually see that the Vine couplers model seems to generate more realistic trajectories compared to this metric. So to conclude, first of all, when we talk about these methods of dimensionality reduction, it is very intuitive, and that's a good point because all positions are distributed along the same line. So we clearly see what are the marginal distribution and how we have this coupler with the dependency between the marginals. We also reduce the dimension by a factor of 2, and it improves the goodness of it. So that's a cool thing. But it also induces wiggles. So that's the methods that like that. And it cannot be applied to 4-dimensional trajectories, unfortunately, so with the altitude and the time. And it cannot be applied also to the trajectory with loops, so with holding patterns and things like that. To actually overcome the difficulty of 4-dimensional trajectories, we came up with an idea of making kind of hybrid method between model-driven methods and data-driven methods. So in that way, we can have the leverage of stochasticity of statistical models, but also the realisticality or the realistically generation of the model-driven methods. For the trajectories with loop, that's just a drawback of our methods. And if you want to overcome this, we actually have to think about a new way to represent trajectory that could actually include those loops. For the statistical estimation itself, we actually see that the couplers generate more atypical trajectory, which is a good point. But the Gaussian mixtures seems to slightly better estimate the density when we look at the E distance. And this is actually due to the fact that the couplers suffer a lot from the high dimensions. Here we used it on 30 features, but in real life, statistician tends to use it on more like 10 features. So that's still a bit too big. To overcome also this difficulty, we can we can also work on the representation space by trying to find some representation of the trajectories that are even in a lower dimensional space in which we have less features, and so it is easier to fit these multivariate distributions. Another way, of course, to improve those couplers is to leverage the flexibility of deep learning in order to look into a more diversified space of functions, and so maybe to have more complex couplers to describe our datasets. So this is pretty much the end of my presentation. Feel free to ask any questions if you have, and thank you.